Welcome to EDU World Space.
For part A of the problem, we're given an acceleration of 35 meters per second squared, a distance traveled of 0.64 meters, initial velocity of 0, and our unknown is the final velocity of the ball. So because we don't have any time given here, and we want to find velocity, we're going to use the kinematic equation v squared is equal to v naught squared plus 2 times the acceleration times the distance traveled. Plugging in our knowns and solving for v, we get a value of v is equal to 6.7 meters per second, which is the speed of the ball as it leaves his hand. Now to do part B, we're going to take our v that we determined here, and that'll become our initial velocity, not our final velocity. So our v naught now becomes 6.7 meters per second. We want the maximum height, and when it reaches the maximum height, the velocity is 0. So our final v is going to be 0 meters per second. Our distance traveled is our unknown in this case. It's what we want to solve for. And our acceleration is no longer 35, it is now negative 9.8, because the only force acting on the ball now is gravity, which causes this acceleration. Again, we're going to use v squared is equal to v naught squared plus 2 times acceleration times the change in distance. We're going to use this one again because we still don't have time involved, and we want to figure out what x minus x naught is, and so this will give us that. Plugging in our knowns and solving for x minus x naught gives us a value of x minus x naught equals 2.3 meters. This is the distance the ball travels, but it's not the maximum height, because we're told the ball leaves his hand at 2.2 meters. So it turns out that x naught is 2.2 meters. When we plug that in and solve for x, the actual maximum height of the ball, we get that x is 4.5 meters, which is the final answer for part B. For part C, we want to figure out the time that he has to move away before he hits the top of his head. And so we have our knowns. We know that x naught is 2.2 meters, the height that the ball's initially left his hand. We know the final height is the height of his head, which is 1.83 meters. We know the acceleration during this whole time is going to be negative 9.8 meters per second squared. And the initial velocity, we also know it's 6.7 meters per second. And the unknown we want to solve for is time. Now we're going to have to use a different kinematic equation because we want time. And so we're going to use x minus x naught is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. So plugging in our knowns and moving things over, I'm able to get negative 4.9 t squared plus 6.7 t plus 0.37 is equal to 0. This term here came from a over 2. X minus x naught led to this, and then v naught 6.7, which led to this term. And I made it this way because now we have a quadratic equation in standard form, so we can apply the quadratic formula. I get negative 6.7 plus or minus the square root of 6.7 squared minus 4, negative 4.9, 0.37. All that's under the square root. And then divide everything by 2 times a, which is negative 9.8. When you simplify this, you get 2 time values. One of the time values is 1.42 seconds, and then the other time value you get is negative 0.05 seconds. This time value is unphysical because it's negative time, and so we're going to throw it out. It doesn't make sense for this process to take negative time. And so this is the actual time that he has to move before the ball hits him on the head. And that's the final answer for part C.